in this video I'm going to be telling you a little bit about complex numbers. Now, this video is intended mostly for people in my multivariable calculus class to serve them as we start to talk about differential equations in that class. But, this could be, if you're just interested. I am assuming that you do have calculus, though, because I'm going to go into Euler's formula and I'm going to prove it for you using a calculus technique. Okay, if you are interested in complex numbers but you don't have calculus yet, I've got a video about complex numbers somewhere in my channel. It's probably under the college algebra playlist. So I think the first thing I want to do is just remind you about the definition of I, right? The imaginary unit. So we just are going to define I is the square root of -1. And historically, I think that's kind of like where this all came from, was that, for a long time people realized that there was not a number that we could square and get -1 back, but they started to think, well, what if there was? What else could I do? And then they started to realize there's actually some really good stuff you can do if you start to just consider what if you did have a square root of -1. Okay, from that we have facts like I squared is -1, I to the third is I to the fourth is equal to 1. Okay? Obviously, I to the first is I, and I to the 0 is 1. So you could take that a little farther and use that to help you figure out what's 1 over I, right? You could also say it's probably I to the 3 divided by I to the 4 is going to be the same as as 1 over I. Okay, so that's just something I'll throw out there. This is something I would need if I was going to prove Euler's formula for you using a Taylor series, but I'm not going to do that. I'm not going to do that in this video. Maybe I'll do that in a separate video. I think that's kind of like what I have typically in the past told people when they've asked me why does this formula work. It's like, just plug it into the Taylor series, it works. But the thing is, I never really told you in AP Calculus that you can plug an imaginary number into a Taylor series. You certainly can, but that was just not something that we had ever even considered, right? Okay, so we know what I is. Let's talk about the complex plane. Okay, so we're going to define C to be the set of all complex numbers. So C is the set of all A plus BI for which A and B are real numbers. And of course, this I is that I right there. Right? Okay, what does this look like? I'll draw you a picture of C. It looks like the XY plane, right? And this is the real line. This is a set of all real numbers right here on what we would consider the x-axis. And then this vertical axis, this will be kind of the imaginary axis, and we can think of that as I times the set of real numbers. So, if this is 1 right here, then this will be I. And we could have, some point out here being A plus BI. And maybe I'll just say that's 2 plus I. Now, the variable that we usually use to denote a complex number is going to be z, and then if you need a second one, probably w. And so what I'll say is I'll call this one z equals 2 plus 1i, right? For example. Okay. I'm also going to need to define the absolute value of a complex number. So the absolute value of z is equal to the square root of a squared plus b squared if z is a plus bi. Maybe I'll write that. Okay, and that kind of makes sense, right? Because the absolute value of a number is its distance from 0. And I could say that the distance here is probably going to be, if this was 2 and that's 1, well, that'll be the square root of 4 plus 1 is going to be the square root of 5. So maybe I'll write that over here. Absolute value of z is equal to the square root of 2 squared plus 1 squared, not the I squared, right? It's the number of i's, right? A plus b. And that's the square root of 5. Okay. What else do I need to tell you? I need to tell you about the complex conjugate. Okay, so if z is a plus bi, then what we would call z bar is equal to a minus bi. Okay, and I'm going to just mention that we call this the conjugate. Okay. Let's see. All right, I'm going to do a little bit of complex arithmetic for you just to remind you that it works like you expect. What I'm going to be wanting to do is probably talk about z is 2 plus I, and maybe w is just I. Yeah, I think that's what I want to do. So, as far as arithmetic with complex numbers goes, okay, we can add these and subtract these. They work just like we expect. We just need to observe like terms, right? We've already said you can't do 2 plus I. It's not like 3I or anything, so we're just going to have to respect that. I don't think I'm going to go into addition and subtraction of complex numbers because it's going to work like you expect. Okay, but for multiplication and division, I'll just remind you, right, we're going to have to maybe use the distributive property. Remember that I squared is -1. Division could be a little tricky if you just didn't already know what to do. And I'm also kind of assuming that you worked with these a little bit in Algebra 2 or some class like that. So as far as the arithmetic goes, if z is 2 plus I and w is equal to, let's see, what am I saying? Oh yeah, I said I. Yes, I know why. Okay, then z times w, or w times z, is equal to I times 2 plus I, right? I can do a little bit of that, which is going to be 2I plus I squared, which is going to be -1 plus 2I, if I wanted to write this in a plus bi form. Okay? But what if I wanted to do w divided by z? Okay, that's really kind of what I was getting at. Like, what am I supposed to do when I get w divided by z? Okay, so w divided by z is going to be I divided by 2 plus I. Right? And then what that's going to mean, what I'm going to need to do, I need to get the I out of the denominator, right? That's really what's keeping me from, having a plus bi. So one nice thing that I can do to take a complex number and multiply it by just something and make sure that it's going to come back a real number is going to be multiplied by its complex conjugate. Okay, so just kind of a fact that I'm going to throw out there, didn't remember to state this earlier. This is something that you could prove on your own if you wanted. Okay, for a complex number z, if you multiply z by z bar, you're going to get the length of z squared. Okay. Z times z bar is equal to the length of z squared. Yeah, just throwing that out there. And then I'm going to use it over here because I'm going to, the length of z, that's a real number. The square, that's certainly also a real number. So I'm going to multiply on top and bottom by the complex conjugate. If I've multiplied by 1, I'm going to change this number. I'm just going to write it in a different form. So I'm going to multiply on top and bottom by 2 minus I. And then I'm going to use the distributive property and, at least on the top, right? It's going to be 2I minus I squared divided by, what's going on here? 2 plus I, 2 minus I, that's the length of z squared. I already know the length of z, that's square root of 5, so square it, that'll be 5. All right, negative I squared is -1. So this is equal to 1/5. Yeah, 1/5 from here, plus 2/5 I. All right. Now, what else was I... Oh, yeah, this was not the example that I was thinking of. Okay. Back to the multiplication. There is something that I do want to show you about the complex multiplication. And I forgot to put it on my note sheet, but it's occurring to me now. And I don't think I'm going to go into too much depth on this. I don't even think I'm going to write down the rule. I am going to point out what's happening though, and tell you that you could use this to really investigate further into the world of complex numbers. So back to the multiplication I did, where I did z times w. All right, and here's my complex plane. Okay. So I know that z was out here. It was 2 and 1. And w was I, which is up just right there on the imaginary axis. So maybe I'll use green for that one. And then when I multiplied them, I'll label that also. When I multiplied them, I got -1 plus 2i. So -1 plus 2i. Now that's interesting. W times z. But what I want to point out to you is that when we did this, hold on, W times z. Yeah, all right. First of all, the length of the product was the product of the lengths, right? Z had a length of square root of 5, W has a length of 1, and W times Z also has a length of square root of 5. Okay? Also, if I looked at, and we're going to be talking about kind of the trigonometry here in a second, if I took this angle, theta, well, and then this angle, and maybe I called it psi or something. The angle up to W times Z is going to be theta plus psi. Okay? So that's what happens when we multiply two complex numbers. We add the angles and multiply the lengths. And that's the de Moivre theorem. And I'm not going to go into that in this video, but that's, you can really use this to kind of like launch off your investigation into complex numbers. You can use that to figure out what the square root of I is. Okay? Just if you think about it, it would be a number that if we doubled its angle and multiplied its length by itself, we would get to I. Or maybe I'll just take that a little further and show you what I'm talking about. So if that's I, right? Now I want to multiply the same thing by itself to get a length of 1. It's going to have to be on, the square root itself is going to have a length of 1, is what I'm saying. So I know it's going to kind of be on this unit circle. And moreover, it's going to have like the type of angle where if I add that angle to itself, I'm going to end up with pi over 2 up here. So it's going to be over here at pi over 4. And so this is the square root of I. And well, we know the coordinates on the unit circle, that's square root of 2 and square root of 2. So the square root of I is equal to, root 2 over 2. I think I was thinking 1 over the square root of 2. Plus root 2 over 2i. And all right, that's all I'm going to say about that, and I'm not going to get too deep into that. Okay. So now I need to tell you about the trigonometric form of a complex number, and then jump in to tell you about Euler's identity. Go. All right. So, without loss of generality, I'm going to assume that I've got a point in the first quadrant, right, where A and B are both positive, but this would be just the same in other places. And suppose I've got a complex number A plus BI. And I'm calling it Z. Okay. Well, you remember polar coordinates from pre-cal and calculus. I can say that this is some distance away from the origin along some angle, right? So I can say that this is, you know, r units of distance away along some sort of trajectory, theta radians above the horizontal, right? And so what I'm going to say is that I can also say that z is equal to r times, well, cosine of theta plus I sine theta, right? Because the x-coordinate is a, which is r cosine theta, okay? And the imaginary component is going to be the y-coordinate is r sine theta. Well, we just say r sine theta multiplied by I. I mean, we're going to go up that way, okay? And so this is, you know, kind of the trigonometric form of a complex number. And then this is something, I don't remember where there's all sorts of ways that you need to be interested in the complex form of a trigonometric number, but of course right now I can't think of them besides, you know, what we're about to do in differential equations. So I remember doing this in my pre-calc class, but I don't remember. Okay, so what was I going to say at this point? Okay, I've written down the trigonometric form. Oh, okay, so I want to really, the idea here is I want to figure out what's the deal with e to the it, right? What happens if I take e to a complex power, or an imaginary power, really, is what I'm going to restrict my discussion to. And you'll see when we go and deal with the complex number situation in differential equations that I really only have to worry about the imaginary component. Is all that I really care about, is all that's going to make a huge difference. So I'm going to, you know, really try to investigate e to the it. Now, at this point, we don't really know the first thing about e to the it, but I'm going to assume that it's a complex number, right? It's most likely going to be a complex number. You know, suppose it was a real number. Maybe it was here. Then it would still be a complex number. But I'm just going to assume for now that e to the it, suppose it's an element of C. Suppose it's a complex number. I'm going to say if it is a complex number, then I'm going to be able to write it in its trigonometric form. So I'm going to say e to the it is equal to r times cosine of t plus I times the sine of t. Okay, then for some r and wait, what is a hold on. That's what I'm going to eventually show you. Pardon me. For some theta, it's going to be r cosine theta plus I or r sine theta times I. Okay. And for some r and theta, okay. And then what I'm going to do is I'm going to take the derivative of both sides with respect to t. Okay. Now, for pretty much any, no matter what you consider e to the t to be, like what's your definition of e to the t? And that's something that I think we only talked about very briefly in AP Calculus, and I don't think we've touched on since. But pretty much regardless of how we're going to, conceptualize e to the t, the derivative of e to the at is going to be a e to the at, regardless of if a is real or complex and whatever. Okay? So what I'm going to do is I'm going to take the derivative of both sides of this equation with respect to t, and I am going to probably just get rid of this. It's just looking like it's going to get in the way. So when I take the derivative of e to the it with respect to t, and I know that's going to involve product rule, so I'm going to need to add in some space. So that's going to be I e to the it is equal to, all right, I'm going to take the derivative of r with respect to t first, because, well, I don't really know how to do that, so I'm just going to call it dr dt, and that seems pretty easy. And then I'm going to leave the other part the same, cosine theta plus I times the sine of theta. And then I'm going to add in, leaving r the same, taking the derivative of this with respect to t. Okay, well, the derivative of cosine of theta is negative sine theta. There would be a d theta dt here, but I'm just going to save that till the end. Plus I times the cosine of theta times d theta dt. Right? And now what I'm going to need to do is probably, what I'm going to try to show you is that for dr dt and d theta dt, like, one of them is going to be 0, meaning that it's a constant, and the other one's going to be, you know, a different constant that we could use to figure out the relationship between it and t. And I'm thinking, yeah, r is the constant, and we're going to see that theta is t. Okay. So, but what I need to do right now is I'm going to need to, I still have t's in here, right? I still have an actual t. Okay, so I need to substitute on e to the it, but I've got a formula for e to the it. Okay, so what I'm going to say is I times r times cosine of theta plus I sine theta is going to be, and then what I'm going to do is I'm going to collect everything that has I'm going to like distribute and separate based on real and imaginary parts, okay, which is a really common trick to do, like an algebra trick to do when you're dealing with a complex number situation, is to equate real and imaginary parts. Kind of similar to, I don't know if you've ever done the partial fractions problems where you end up having higher powers. Idea is you're not going to get an I from an expression that doesn't have any i's in it, right? Okay, so I'm going to say, let's do all of the things that have no I in them together. Okay, so that's going to be dr dt cosine theta minus r sine theta d theta dt. So maybe I'll just write that. Cosine theta dr dt minus r sine theta d theta dt. And then I'm going to have a plus sine theta dr dt, and I'm going to save the I till the end. Sine theta dr dt, what is it going to be? Plus r cosine theta. Wait, okay. There is not supposed to be a dr dt there. I think that's supposed to be an r. Let me just take a second and step back and look at this. Okay, plus I sine theta. No, that was right. Okay, so what I'm doing is I'm collecting all the things with the I, and I'm going to hold that on that I last, and I have a sine theta dr dt. Okay, so it just didn't look right, I feel like. Okay, then I'm going to have a r cosine theta r cosine theta d theta dt. Yeah, that was tricky. Times I. And I am going to pause and double check this to make sure I haven't made an algebra error. I feel like I'm a little lost in the algebra right now. All right, yeah, we're all good, but I'm going to want to distribute this IR so I can just like kind of equate real and imaginary parts. So I'm going to kind of do that. So when I distribute this, I'm going to have an IR cosine theta. So I'll just kind of keep square down here. I'll have an IR cosine theta, and then an I squared, that's a -1 R sine theta. So minus R sine theta. Okay, so I'm going to actually replace that here to kind of save some space. So I've got -R sine theta plus IR cosine theta, so R cosine theta I. Yes. All right. And then I'm going to equate real and imaginary parts. Okay, so let's just maybe use blue for the real part, negative r sine theta needs to be equal to cosine theta dr dt minus r sine theta d theta dt. And then I will also need the imaginary part, r cosine theta, to equal sine theta dr dt plus r cosine theta d theta dt. And it's like, how is that going to actually work out? But if we write these kind of like on top of each other, I think you'll be able to see what's supposed to happen here. All right, so I've got, maybe I'll go over here and actually continue working in blue and pink, so you see what I'm saying. Negative r cosine theta is equal to cosine theta dr dt minus r sine theta d theta dt. Okay. And then I've also got, r cosine theta equaling sine theta dr dt What's that? And then probably what I'm going to do is set both of these equal to 0. Hold on a second. I did this differently in my notes, and maybe I just need to reconcile it. All right, so I was thinking about this for a second, and doing a little bit of the algebra for you, right? I subtracted the arc cosine theta over here and factored out arc cosine theta. I mean, you can look at this and see that this is the derivative with respect to t of r sine theta, right? And then this would be the derivative with respect to t of r cosine theta. And I feel like there's a bunch of different directions I could go here, but I think rather than getting too bogged down in the algebra, I'm going to say, hey, look, okay, if dr dt was 0 and d theta dt was 1, both of these equations would simultaneously be true, right? I think that you could go in and do some elimination and some more hardcore algebra and see that that like is kind of a necessary condition. But I think that I'm going to just stop here and say, look, this is going to be true if d theta dt is 1 and dr dt is 0. Okay, and both of these are situations that we know how to deal with. If dr dt is 0, then r is equal to a constant. And if d theta dt is 1, then theta is going to be equal to t plus some other constant. Okay. So I need some sort of initial condition. And so what I got to think of is what happens when t equals 0. That's pretty easy to see. So when t equals 0, okay, well, e to the 0 is 1. So that would mean that, well, e to the 0, 1 is equal to r times the cosine of 0 and then the sine of 0. Okay, so r is equal to 1. Wait. E to the 0 is, oh, no. Pardon me. Okay, r is pretty clearly 1 if e to the t is 0, just because that's going to be, or if t is 0, e to the t is 1, so you're 1 unit away. But that's what I probably want to be saying is e to the it is e to the 0 is 1, and we know where 1 is on the complex plane. It's in terms of r and theta, r is 1 and theta is equal to 0. So r equals 1, theta equals 0. So if r is going to be a constant, r has to be 1. And if theta is 0 when t is equal to 0, then theta needs to equal t, which is kind of what I'd hope to show in the first place. So the conclusion is that, well, this has got to go now, is that e to the it is cosine of t plus I times the sine of t. Yeah, I'm not sure I just love this proof that much more than the Taylor series way, but the Taylor series way is just like kind of what I always give, and so I figured I'd mix it up for this video. And this is pretty much all I need you to know about complex numbers, at least for the time being. If there's anything else we're going to need, I'll come back and record another video and just kind of like throw it in the differential equations playlist right before you need it.